All right, so the universe, right? It just keeps throwing up these really mind-bending questions like why does time only seem to go one way? What even is reality? And then, gravity, this invisible thing that shapes everything. Oh, and maybe the weirdest one for me, why does moving super fast actually slow down time? And these aren't just, shower thoughts.
Hmm.
These are like fundamental mysteries that have puzzled the smartest people for, well, forever.
And what's so cool about all this, for you listening, is that we're talking about the very essence of physics here, time and gravity. They aren't just abstract ideas, they're deeply intertwined, and they reveal just how interconnected the universe really is.
Totally. And that's exactly what we're diving into today, time and gravity. You're the kind of person who wants to get the big picture, understand the core concepts without getting bogged down in the weeds. So consider this your crash course in, well, some pretty mind-blowing stuff.
And if we think about this from your perspective as a learner, you want efficiency, right? Our aim here is to distill the most essential insights from centuries of scientific exploration into these forces. Imagine taking this massive library of knowledge and extracting the most potent information just for you.
Okay, so what's the plan for this deep dive? We're going to start with Newton's work on gravity, the bedrock of so much of what we know. Then we'll jump into Einstein's revolutionary theories of relativity, both special and general, which completely changed how we see space and time. We'll even touch on some alternative ideas that challenge Einstein. And then we'll explore the very real, practical consequences of time dilation, like how it affects our technology and space travel. And finally, we'll wrestle with the mystery of why time seems to only move forward, delving into entropy, and then we'll take a peek at some cool new findings from CERN that are pushing the boundaries of what we know about the universe. Ready to go?
Yeah, I think what's really important to remember from the outset is that, well, our everyday intuition about these things can often clash with the deeper scientific explanations. So it requires a shift in perspective, seeing the familiar in a whole new light.
For sure. Okay, so
Sure.
let's start with Sir Isaac Newton. The story goes that he saw an apple fall, and boom, this flash of insight about gravity. And you know what? His understanding of gravity was a huge achievement. I mean, it was so accurate that we used it to figure out how to get to the moon. But as awesome as that is, it turns out Newton's view of gravity is more of a really, really good approximation.
Yeah, and that's a crucial point. So while Newton's laws perfectly describe how objects move under the influence of gravity, which is how we did all those amazing calculations for things like lunar missions, they don't actually explain what gravity is. It's like they describe the effect, but not the cause.
Right. And Newton himself seemed to kind of acknowledge this limitation. He basically said, look, I can show you how the planets and stars and comets move according to these laws, but asking how or why gravity exists, that's a question for something bigger. So he was kind of okay with leaving that fundamental why unanswered.
Right. He gave us the tools to predict and calculate, but the deeper nature of gravity was outside his framework. And that's where Albert Einstein enters the scene. This is where we see a true revolution in how we understand gravity.
Mental fireworks time. Albert Einstein. The name itself is like synonymous with genius. And in the early 1900s, he really did rewrite the rules of physics. It all began with his theory of special relativity, which he published in 1905. This is the first major crack in our traditional understanding of space and time.
And what's really remarkable is that special relativity came from a few fundamental insights. The most important being that the laws of physics are the same for everyone moving at a constant speed relative to each other. And also that the speed of light in a vacuum is constant, no matter how you're moving or how the light source is moving. These ideas, seemingly simple, have incredible consequences for how we see the universe.
And one of the most mind-boggling of those consequences is, well, time dilation. The idea that time isn't the same for everyone. It can actually slow down or speed up depending on how fast you're moving relative to someone else.
Absolutely. To really get this, the light clock thought experiment is super helpful. Imagine a spacecraft with two mirrors facing each other, and there's a pulse of light bouncing between them. For someone inside that spacecraft, the light's path is straight up and down. The time it takes for the light to travel between the mirrors is constant.
Okay, I'm picturing it. Light just bouncing up and down.
Now, imagine someone outside the spacecraft watching it zoom by at, close to the speed of light. For them, the light still has to travel between the mirrors. But now, because the spacecraft is moving sideways, the light's path isn't just vertical anymore, it's diagonal. It has to travel a longer distance.
Ah, okay, I see. The light has to travel further because the mirror is moving away as the light travels.
Exactly. Now, here's the key. The speed of light is the same for both the person inside the spacecraft and the person outside. But the light has to travel a longer distance for the observer outside. And since speed is distance divided by time and the speed of light is constant, the only way for this to work is if time itself is different for the two observers. For the person outside, time on the spacecraft must be passing more slowly. That's time dilation. It's mind-blowing, but the constant speed of light forces time to be relative. It's a fundamental shift in how we see reality.
Whoa. So the person on the spacecraft, they wouldn't feel time slowing down, but to us watching them zip by, their watch would be ticking slower.
Exactly. And this isn't just some theory. Time dilation has been confirmed in experiments, including in particle accelerators like the Large Hadron Collider or LHC. Particles there move at crazy speeds, and scientists have to account for time dilation to get accurate measurements.
Wow, so it goes from a thought experiment to something we have to factor in to real science.
Yeah.
And there's more, right? There's length
Yeah.
contraction, too.
Right. Special relativity also predicts that objects moving at high speeds appear shorter in the direction they're moving, at least from the perspective of someone standing still. It's another consequence of the constant speed of light and how space and time are connected.
So not only would a speeding spacecraft's clock run slow, but the spacecraft itself would look squished in the direction it's going.
Yep, that's the counterintuitive reality that special relativity reveals. And then, of course, there's the most famous equation in physics, E and c squared.
Einstein's big one. Energy equals mass times the speed of light squared. It's everywhere.
And it comes directly from special relativity. This equation tells us that mass and energy aren't separate things, but they can be converted into each other. A tiny bit of mass can become a huge amount of energy, and vice versa. This is what powers nuclear reactions, including the sun.
So special relativity isn't just theoretical. It has real-world implications, like the particle accelerators you mentioned. Anything else?
Absolutely. Think about GPS. Those satellites orbiting Earth are moving pretty fast relative to us on the ground, and they're also in weaker gravity. Both of those things cause time dilation. If GPS didn't account for these tiny differences in the flow of time, the satellite's clocks actually run a bit faster because of special relativity. Even though general relativity has the opposite effect, well, our navigation systems would be way off, drifting by kilometers every day. So that pinpoint accuracy we rely on, it's thanks to Einstein's relativity.
That's wild. So all that pinpoint accuracy we take for granted is actually thanks to Einstein's mind-bending theories.
Exactly. Special relativity forces us to rethink some pretty basic ideas about time and space. Time isn't absolute, it's relative to your motion, and the speed of light is the ultimate speed limit in the universe.
Okay, so Einstein blew our minds with special relativity, but he wasn't done, was he? He gave us general relativity in 1915, which took our understanding of gravity to a whole other level.
Right. Special relativity dealt with observers moving at constant speeds, but general relativity brought in gravity and acceleration. It's a truly revolutionary view of the universe.
And the big idea here is that gravity isn't a force, like Newton thought, but a curvature of space-time caused by massive objects. That's tough to wrap your head around.
It is, but here's an analogy. Think of space and time not as separate things, but as this interconnected fabric. We call it space-time. Now imagine putting a bowling ball, representing a massive object like a planet or star, on a trampoline. It creates a dip, right? If you roll marbles nearby, they'll curve toward the bowling ball, not because they're being pulled by some mysterious force, but because they're following the shape of the trampoline. Space-time works kind of like that. Empty space isn't just empty, it's an active player, shaped by mass and energy, and it dictates how things move.
So, the Earth orbits the Sun not because the Sun is pulling it, but because the Sun's mass warps the space-time around it, and the Earth is just following that curve.
Exactly. General relativity gives us a much more accurate explanation for how planets move, including the elliptical orbits, something Newtonian gravity couldn't quite get right.
And there was that famous experiment during a solar eclipse in 1919 that really proved general relativity, right?
Absolutely. Sir Arthur Eddington led an expedition to observe a solar eclipse. According to general relativity, the sun's gravity should bend the light from distant stars as it passes by. During the eclipse, when the sun's light was blocked, they could see those stars, and their positions were shifted, just as Einstein predicted. It was a huge confirmation.
Wow, they saw space-time being warped right before their eyes. And general relativity messes with time too, doesn't it? Gravitational time dilation.
Yeah, gravitational time dilation says that time runs slower in stronger gravity. So if you were hanging out near a black hole, your watch would actually tick slower compared to a watch far away from the black hole.
So gravity not only pulls things together, but it also stretches time. That's crazy. And general relativity predicted the existence of some pretty extreme objects too, like black holes.
Right. Black holes are regions in space-time where gravity is so strong that nothing, not even light, can escape. They are the ultimate consequence of the warping of space-time predicted by general relativity.
And general relativity helps us understand the big picture too, like the structure of the universe and the Big Bang.
Absolutely. It's the foundation for our understanding of cosmology and how the universe evolved from that initial state. Though it's funny, Einstein himself initially added a term called the cosmological constant to his equations because he couldn't accept that the universe was expanding. He later called it his biggest blunder when observations proved him wrong.
The irony. Even Einstein had his doubts. What about gravitational waves? Those sound like something straight out of sci-fi.
They do, but they are another key prediction of general relativity. They're ripples in space-time caused by the acceleration of massive objects, like when black holes collide. The first direct detection of these waves in 2015 by LIGO was another major win for Einstein's theory.
So general relativity has passed every test we've thrown at it. But are there scientists who think Einstein might not have had the whole picture? Are there alternative theories out there?
Well, that's the beauty of science, always questioning and exploring. While general relativity is super successful, some scientists are exploring alternative. One of the most popular is modified Newtonian dynamics, or MOND.
MOND. What's the gist of it?
Basically, MOND says that gravity acts differently at very low accelerations compared to what Newton's laws predict. Proponents of MOND think this might explain some observations about galaxy rotation without needing to invoke dark matter, which is this mysterious stuff we haven't directly observed. So they're trying to solve the dark matter mystery by tweaking gravity itself.
So they're trying to solve the dark matter mystery by tweaking gravity itself.
Yeah, that's the idea. The whole debate around dark matter and dark energy is really interesting. Some folks who like alternative gravity theories argue that maybe we don't need these mysterious concepts if we just understood gravity better.
But not everyone agrees, right? Not everyone thinks Einstein was missing something fundamental.
Exactly. Lots of experts still think general relativity is the best we have, and that maybe there are other factors we haven't discovered yet, like things related to quantum gravity, that could enhance our understanding without needing to totally rewrite Einstein.
And these alternative theories, they don't just cull them out of thin air, right? They get put through the scientific ringer.
Oh, yeah. The scientific community is super rigorous. Any new theory has to be tested against observations and experimental data. And while some of these alternative theories have some support, none of them have dethroned general relativity as the champ.
It's good to know that the questioning and testing is all part of the process. Okay, so we've gone through some mind-bending theories. Let's bring it back down to Earth, or maybe blast off into space. What are the practical implications of time dilation, especially for things like space travel?
This is where the theory gets real. We all dream of traveling to distant stars, but the distances are just so vast. And then there's the speed of light limit. Those are big hurdles.
Yeah, even the closest stars are light years away. It would take forever to get there, even at super high speeds. And that brings us back to time dilation and the famous twin paradox.
Right. The twin paradox is a classic thought experiment. Imagine two identical twins. One stays on Earth, and the other hops on a spaceship that travels close to the speed of light to a distant star and back. Because of time dilation, the traveling twin would age more slowly than the twin who stayed on Earth. They'd come back younger. It makes you wonder about the sacrifices of interstellar travel, not just for the traveler, but also for the people they leave behind.
It sounds like a sci-fi movie,
Yeah,
but it's real physics.
it is. How much time dilation you get depends on the speed and the distance. The closer you get to the speed of light, the bigger the effect. For interstellar trips, the time difference could be huge. Astronauts could return to Earth having aged only a few years, while decades or even centuries have passed on Earth.
That's heavy stuff. Not just the technical challenges, but also the personal impact on the astronauts. You mentioned earlier that time dilation affects technology here on Earth too, right?
Yeah, even in high-speed aircraft, the computers and communication systems have to be super precise, and even tiny amounts of time dilation can have a measurable effect. Of course, these effects are much smaller than what you'd see in near light-speed space travel. And like we talked about before, GPS systems have to account for time dilation in the satellites to work properly.
So even our everyday tech relies on these mind-bending ideas about relativity. Okay, let's tackle another big one. Why does time seem to only move forward? We remember the past, we think about the future, but we never seem to go backward in time. What's up with that?
This is one of the deepest questions in physics. To understand why time goes one way, we need to talk about entropy.
Entropy. That sounds kind of technical.
Basically, entropy is a measure of disorder. Think of it as the tendency for things to get more mixed up and less organized over time. The second law of thermodynamics says that in a closed system, entropy always increases or stays the same. It never decreases on its own.
Okay, give me some examples. How does entropy work in our everyday lives?
Imagine a deck of cards, all neatly arranged by suit and number. You shuffle it, and now the cards are all mixed up. The shuffled deck has more entropy than the ordered one. Or think about an ice cube melting in a glass of water. The ice melts, and the cold water mixes with the warm water. It becomes more uniform, less organized. Entropy has increased. Or when you stir milk into coffee, they mix. You never see them spontaneously unmix.
Right, things tend to go from order to disorder. Makes sense in our everyday world. But what about the microscopic world, like with atoms and particles?
It's interesting. At that level, the basic laws of physics seem to work the same forwards and backwards in time. Imagine filming two billiard balls colliding. If you played the film backwards, the physics would still look right. This is called time reversal symmetry.
So the basic rules don't care which way time goes. So where does the arrow of time come from then?
Well, the apparent contradiction comes from the starting conditions of the universe. It began in a very low entropy state and the huge number of things interacting in the macroscopic world. As the universe evolves, the number of possible disordered states is vastly greater than the number of ordered states. So statistically, things tend toward disorder.
So it's a numbers game. Like, there are just way more ways for things to be messy than neat.
Exactly. And this increase in entropy at the macroscopic level is what we experience as the arrow of time. It also connects to our brains. We process information from past memories to make predictions about the future. Our experience of time flowing one way is tied to this increase in entropy.
That's a deep connection. And it has implications for philosophy too, right? Like our understanding of cause and effect and how we see the past as fixed and the future as open.
For sure. The one-way flow of time is fundamental to how we understand causality and even reality itself.
Okay, we've gone from Newton's apples to Einstein's warped space-time and the relentless march of entropy. Now let's switch gears and talk about the latest buzz from the world of particle physics, specifically CERN. I hear there's been a unique finding that's got scientists buzzing.
Yeah, CERN, the European Council for Nuclear Research, is at the forefront of particle physics, and the Large Hadron Collider is their big star. And lately, there have been some interesting results coming from the LHC that could change how we understand the universe.
For folks who don't know, CERN is this huge research facility, right? With a giant 27-kilometer ring buried underground. It cost billions of dollars to build. But it's also been responsible for major discoveries like the Higgs boson.
That's right. The LHC works by smashing particles together at incredibly high speeds, and then scientists study the wreckage to see what's inside. The Standard Model is our current best description of all the fundamental particles and forces, so finding something that doesn't fit is a big deal.
And this unique finding, what is it exactly? Something about beauty quarks acting weird.
Right. Scientists at the LHC have been studying how beauty quarks, which are these unstable fundamental particles, decay. According to the Standard Model, they should decay into muons and electrons with roughly equal probability.
But that's not what they're seeing.
Nope. The data shows that beauty quarks are way more likely, like 70% more likely to decay into muons than electrons. That's a big anomaly. It doesn't fit with the Standard Model.
So this is a big deal because it suggests there might be something missing from our current understanding of physics.
Exactly. It hints at the possibility of new physics beyond the Standard Model. Maybe a new fundamental force or a new particle that interacts differently with electrons and muons.
They've even given this hypothetical particle a name, right? Something like Z prime.
Yeah, the idea is that there might be a new particle called the Z prime boson or maybe some other new force that affects these decays in a way the Standard Model doesn't predict. We haven't directly detected this particle yet, but it could explain what we're seeing.
And if this is confirmed, what could it mean for our understanding of the universe?
It would be huge. It could help us solve mysteries like dark matter, the Higgs boson, and maybe even help us unify all the fundamental forces of nature into one grand theory. And what makes this particularly interesting in the context of our discussion is that these particles and their interactions are governed by space-time itself. So this strange behavior could point to something deeper about reality, maybe even about how time and gravity work at the most fundamental level.
It's amazing to think that these tiny particles smashing together in a giant ring could hold the key to such huge questions. And speaking of the LHC, I saw a quote from Elon Musk about it.
Yeah, Elon Musk called it the largest and most powerful particle collider ever built. It's an incredible feat of engineering. It's located near Geneva on the border of France and Switzerland, and it operates at crazy high energy levels. It can collide protons and also heavier ions like lead.
And its main goal, as you said, is to test these physics theories and study particles like hadrons.
Exactly. Hadrons are like the building blocks of matter. They include protons, neutrons, and other particles like mesons. The LHC lets us recreate the conditions just fractions of a second after the Big Bang, giving us a glimpse into the early universe.
And finding the Higgs boson back in 2012 was a major triumph for the LHC, right?
Absolutely. Discovering the Higgs boson was a landmark achievement. It confirmed a key prediction of the Standard Model and explained how fundamental particles get their mass through the Higgs field.
And the research into the Higgs boson is still going strong.
Yep. Scientists are still studying its properties in detail, and there are plans to upgrade the LHC to make it even more powerful, which could lead to finding other types of Higgs bosons predicted by theories beyond the Standard Model.
The term God particle has always been kind of catchy. Where did that come from?
Well, the nickname God particle actually started as a slightly less reverent term, goddamn particle, coined by physicist Leon Lederman because it was so hard to find. The publisher of his book changed it to God particle, and it stuck.
So it's not about divine intervention, but about how crucial and elusive the Higgs boson was.
Exactly. The Higgs field and the Higgs boson are fundamental to the existence of mass and matter and the interactions we see in the universe. Without them, things would be very different. And the search continues for more Higgs-like particles and a deeper understanding of the Higgs field itself.
This is fascinating stuff. But I've also heard some, let's say, less conventional theories about CERN, like conspiracy theories.
Unfortunately, yeah. Because CERN is so big and complex, it attracts conspiracy theories. Some people think they're trying to open portals to other dimensions or cause the Mandela effect. CERN, of course, says its goal is purely scientific to understand the universe.
Right, focusing on scientific discovery, not interdimensional portals. And I also heard they detected neutrinos at the LHC for the first time.
Yeah, that's another cool development. One of the experiments at the LHC, called PHASER, detected high-energy neutrinos produced in the collisions. They saw a bunch of neutrino interactions with high precision, which can teach us about astrophysics stuff, like what happens inside stars and supernovae.
Neutrinos are those super elusive ghost particles, right?
Right. They're produced in various nuclear processes, but they barely interact with matter, making them super hard to detect. But now the LHC can study them, opening up new avenues for research.
And all this brings us back to that unexpected anomaly detected in July 2022. It's a puzzle scientists are still working on. Seems like the universe is full of surprises.
For sure, we've come a long way, but there's still so much we don't know. Experiments like the ones at CERN keep pushing the boundaries of our knowledge, and sometimes we find things that challenge our current understanding.
So there you have it. A wild ride through time and gravity, from Newton's insights to Einstein's revolutions and the cutting-edge research happening right now at CERN. You, our listener, wanted to learn quickly but deeply, and I hope this deep dive has given you a shortcut to understanding these complex and fascinating topics.
I think the takeaway here is the interconnectedness of everything. Time and gravity aren't just separate ideas. They're woven into the fabric of space-time, shaping everything from the tiniest particles to the largest structures in the universe.
Absolutely. And on that note, here's a final thought to ponder. Could those strange anomalies they're seeing at CERN point to an even deeper connection between time, gravity, and the fundamental nature of reality than we currently grasp? What other seemingly fixed aspects of our universe might turn out to be more complex and surprising than we think? Maybe what you've learned today will inspire you to explore these questions even